Hi, my name is Lucky Obuefia, and this is my Lab 6 about magnetic braking with Faraday's Law for Physics 2212. So, for an introduction to Lab 6, the purpose of this lab was to investigate Faraday's Law by dropping a magnet through a tube of conducting material. So, we're going to explore the connection between essentially changing magnetic fields, or otherwise flux, and the induced electric fields that they produce. The results of the experiment showed conclusively that the magnet does in fact fall slower through the conductive tube due to induced currents, and the time was averaged out to be about 1.47 seconds. And this was with the magnetic dipole actual model that we use predicting a fall time of about 0.74. So there is a discrepancy, but we will get into that. So there are some key concepts and physics principles that we need to be able to proceed, starting with Faraday's law, which says that an EMF can be produced by changes in magnetic flux. The Biot-Savart law says that a magnetic field created by current elements is given below by the equation, and that's just going to be the integral over a path loop E times dl. And Newton's law is just going to relate the forces and how they'll all add up when factoring in forces like gravity, but that is something from Physics 1. So there are some additional conditions that we had to measure in the lab, as you can see on the picture on the right. So the system is going to include the magnet and the aluminum foil tube. The tube has its own properties, length, radius. The magnet has its own mass. And then that dipole moment from lab 4 that we're going to use is 3.96 amps per meter square. Some of the assumptions that we need to use are that there is negligible air resistance, the tube is uniform, and there is no interference by devices nearby. So to get our averages, we dropped the magnet through this tube about 5 times. Some of the values that we got were 1.38 seconds, 1.49 seconds, 1.52 seconds, and 1.44 seconds, and 1.45 seconds. We got these numbers by recording it and going back, replaying the video, and using a stopwatch to get these times, and then the average was found. So taking a look at our computational model, there is a lot to unpack. We had to calculate the induced currents and then compute a magnetic force and then update all of this using Newton's second law. So in that first picture, we just have some of the geometry of the tube and just its properties like length and width. Then we had some physical constants that we needed to define, like the force of gravity. And then lastly, some properties of the magnet, including its mass and the magnetic dipole moment of 3.96. Here are some more calculations and parts that we needed to be able to get the numbers that we did. So firstly, starting with creating that dipole moment, that is found with that first screenshot. The second one was going to give the force of flux, which is found with that equation in the upper right corner. Next, we have the current in the ring that was calculated using the third line given by the flux over the radius of the ring. And then lastly, the force, the total forces, including gravity and the magnetic force that we used by calculating it earlier in image 1. So these are the results that we got from the computational model. As you can see, we got a time of about 0.764 seconds. And there is quite a discrepancy from the observed time, but again, we'll touch on that. Both still overall showed that the magnet did in fact get slowed down by induced currents. There were again large differences. However, it was accurate overall in representing Faraday's law in saying that the magnet itself would experience a force when dropped through a current carrying element such as the aluminum foil. Now, to the degree of which has not been touched on, but it does in fact follow Faraday's law. So of course there was a discrepancy in the numbers, so there are some possible sources of error that we're going to touch on now. Some of these can of course be measured inaccuracies, including tube dimensions. We know that that force is inversely related to radius, so that term being even a little bit off can produce varying numbers. Some of the assumptions were idealized, like no friction. For example, the magnet could have been touching the sides of the aluminum foil wall, which again is cardboard. Not only that, but air resistance. Lastly, human error could have played a role in timing, as it wasn't too scientific of a method that we used. And additionally, that the dipole moment calculation from the prior lab could have been incorrect. So for some of the additional questions, firstly, if the resistivity approached 0, the magnet would fall extremely slow due to the stronger currents inside of the current element, because obviously if the resistivity is lower, the current will be higher. If there were any holes or slots in the tube, that would disrupt the ring current and essentially cause a break in the force. And this would reduce, quote unquote, the braking effect, and the magnet would come out the other end faster. So Faraday's law does accurately predict the slowed magnetic descent of a magnet, which was reflected by our results observationally and computationally. Thank you for your time.